Hello, and welcome to a very special bonus episode of our regularly scheduled worksheet walkthrough. So in this episode, I am going to talk a little bit more about Dijkstras from a more theoretical perspective. There are a lot of things about Dijkstras that we just take for granted. We say, okay, well, when you pop a node, you must have found the shortest path, or you can't have negative edge weights in Dijkstras. But I seek to, in this video at least, help you understand from a theoretical perspective a little bit why we can't have these things, why we can say we have these properties. This stuff is definitely a bit out of scope of the class, so don't worry about it that much. That's why I'm not labeling it as a worksheet video. But if you are interested in contextualizing Dijkstras a little bit more, or if you feel like you really have the mechanics of Dijkstras down, but you're a little uncomfortable just doing the mechanics and not understanding why these things work, then this video is for you. This is also a great video later to come back to, I guess. So we're going to do this, basically, by looking at Dijkstras as a modified form of BFS, because that's fundamentally what it is, basically. And if we look at it this way, I think it becomes pretty intuitive to address these two questions of why is it the case that when we pop a node, we have found the optimal path, and why can we not have negative edges in general in Dijkstras? Okay, so before we do that, let's review a little bit of how DFS actually works. So BFS would work on a graph that looks like this, basically, right? Let's say that this right here is our starting node, and we want to BFS the node. Now, this is something similar to what I did in the last worksheet video, but one way you can look at BFS is it's something that radiates out from a starting node. So in other words, if we are in this starting node, we are going to radiate out in a series of bands searching other nodes. I can't draw very well, but it's going to look more or less like this, right? So we have 4 bands. Inside of this band is everything that is 0 units away from our starting node. Inside this band is everything that is 1 unit away from our starting node, everything that is 2 units away from the starting node, and everything that is 3 units away from our starting node, right? Keep in mind, this is a general BFS, so there are no edges, there are no edge weights on this graph, right? When we say distance, we strictly mean the number of nodes you have to traverse in order to get to a given node. Okay, so you see we have these loops, and if we do a BFS ordering of these nodes, it would be something like this, and then this, and then this, and then this, right? We're going to investigate everything that is 0 away, and then everything that is 1 away, everything is 2 away, and everything is 3 away. And we'll break ties out arbitrarily in between, right? So radiating out from a center point. That's very, very similar to what we're doing in Dijkstras. And in fact, in Dijkstras, we are doing the exact same thing, except instead of radiating out from everything based off the number of nodes you are away, you're radiating out based off the distance you are away, right? So basically, if we look back up at this problem that we just did with Dijkstras, right, I can tell you pretty quickly that the nodes that we're going to start looking at, if we look at the nodes in order of how they're going to get popped, we're going to pop off first A because we start there, and then B, then we're going to pop off D, and then I can quickly see that we're going to pop off C, and then E, and then F, and then G. How can I do that in my head? I'm not running a priority queue in my head. All I'm doing is I'm keeping this fact in mind, right? In BFS, we investigate everything that's 0 units away, then everything that's 1, then 2, then 3. And in Dijkstras, we're going to do the exact same thing, except we're going to use distances. In other words, we're going to investigate every path that is 0 units of distance away total, then everything that is 1 unit away, 2 away, 3 away, 4 away. In other words, the first path we're going to look at Dijkstras is trivially the 0 length path, which is from the initial node. Then what we're going to do is we're going to say, okay, are there any paths in this graph that start at node A and go anywhere else in the graph that are of length 1? And there's one right here. Therefore, this is the next path we're going to investigate, right? And we haven't investigated B yet, so we're going to look at B, right? Then I'm going to say, after we do that, hey, are there any paths that are length 2 away in Dijkstras? Well, here's a path that's length 2 away. Are there any that are 3 away? No. Are there any that are 4 away? Yes. Here's one. Are there any that are 5 away? Yes. Here's one. Any that are 6 away? Here's one, et cetera, et cetera, et cetera, right? So I can tell you the order of traversal of nodes that we're going to do in Dijkstras, not by creating priority queues, not by running all this algorithm, but just by just visually inspecting the graph and saying, okay, any path that is 1 long, any path that is 2 long, any path that is 3 long, 4 long, et cetera, right? Increasing in that way. And that's what I mean by radiating out. And that's why we can see there's a correlation here between BFS and Dijkstras. Another way to think of it is let's redraw this little graph here I have as an example as a BFS graph, or a graph that we can run BFS on, and it will give us the same basic result that we want. Okay, so if you look at this graph, we see that if we were starting at A, right, and we traverse this graph, first thing we're going to pop A, then after we pop A, we're going to pop C, then we're going to pop B, and then we're going to pop D. You can see that the shortest path is A to B to D, right? And you can see that this is the kind of classic example of where Dijkstra's is going to be really, really useful, because you can't just locally say, hey, what is the shortest path out of A? Because if you just took the shortest path out of A and then went to here, you would end up with a longer path than if you took the thing that's initially longer, right? In other words, the shortest path is 3, and we're going to pop the nodes in order of C, then B, then D, coming from B, not coming from C. Okay, let's redraw this graph in a way that we can run BFS on it, and it's going to give us basically the shortest path. And what I'm going to do is I'm basically going to just replace the edges with additional nodes to basically carry out the weight. Okay, so I'm going to redraw this graph that we have here, except I'm going to redraw it in a way such that we have unweighted edges. And rather than saying we have, you know, a weight to edge, we're just going to have 2 separate edges in between. So for example, if we redraw A and B and we want to draw an edge between A and B, I'm not just going to say, okay, it has an edge that's length 2. What I'm going to do is I'm going to do something more like this, right? I'm going to insert one more node. I'm drawing it as a small node just to differentiate it from the big nodes. And instead of having an edge of length 2, we're going to have 2 edges here, right? It's almost as if every edge is actually length 1 and we just have 2 of them, right? Generalizing that process out, if we want to draw from A to C, we're just going to draw directly from A to C because there's only one edge between A and C. If we want to draw to D, we're going to draw like this, right? So now we have 3 edges between C and D. And if we want to draw from B to D, we'll just draw like this because the length of the edge from B to D is 1, right? So basically, I have redrawn this graph, except now it's unweighted, but the kind of all the information is still being passed over, right? We still see that there's a number of edges we need to traverse to get anywhere. Okay, so remember, in Dijkstra's, this graph on the left was traversed in the order A, B, C, and then D. And what's more is that we got to D via B, right? Because we're going to know that in the end, our shortest path to get from A to D is A to B to D, right? Okay, so now let's run not Dijkstra's, but just a standard BFS on this graph over here. Okay, well, first we're going to start at A and we're going to investigate everything that is 0 away from A, which is just A. Then we're going to investigate everything that is 1 away from A, which is C, and this intermediate node, which we're not going to count because it's just kind of a placeholder, right? Oh, I just realized I wrote this wrong. This is A to C to B, which is this. But so we're going to count this intermediate node right here, right? Now we're going to look at everything that is 2 away, which are these 2 things. Now we're going to look at everything that is 3 away, which is these things, right? And notice that D is 3 away, but it's not 3 away in terms of C, it's 3 away in terms of B, right? It's 3 away because it's 2 to B and then 1 additional to C, right? Whereas it would be 4 if we wanted to go this way. So in other words, basically what we see here is that if we run a BFS traversal like this, it just investigates paths in increasing order of length until we get to D. So that's why there's a similarity here. Okay, so now let's actually answer these questions right up here that I posed a little bit, where I said, okay, why is it the case that when we pop a node for the first time, we know that it is the shortest path possible? Well, you can think of it again as this idea of radiating out in a BFS. Again, in Dijkstra's, what we're really doing is we're checking every path that is length 1, then every path that's length 2, every path that's length 3, 4, 5, etc., etc. And we're checking nodes as they fit into that pattern. Okay, so if we look back up at the top here, why is it when we pop C, we know that the shortest path to C is 4? Okay, because first thing we're doing is we're checking any path that is length 1, which is going to be this path. We're checking any length 2 paths, which is this path. We're checking any length 3 paths. There aren't any. Then we're checking any length 4 paths. Notice that the first time we see C in one of these paths we are checking, it is when it is a length 4 path. This is why it is the shortest path to C. Because remember, we're checking paths in ascending order. So if there were any other path shorter, right? If there was a length 3 path to C, we would have checked it before the length 4 path. In other words, we would have already seen C, right? But we know because the first time we see C in a traversal is when we have this specific path here that is of length 4, we know there is no shorter path, right? There could be longer paths to C, but that doesn't really matter because we're only checking for the shorter ones. Okay, this also leads me to the second point. Why can we not have negative edge weights in general in Dijkstras? Well, because we know this ability we have to say that, okay, C is, minimum 4 because we popped it and the first time we popped it was distance 4. The reason we can do that is because we are checking path length successfully. We're checking every path of length 1, then 2, then 3, then 4, then 5, et cetera, et cetera, et cetera. So the problem is once you start putting negative edge weights in there, you mess up this guarantee that we're checking paths successively. In other words, you might check a path of length 1, then 1 of 2, then 1 of 3, then 1 of 4, and then 1 of 2 again. And then you've messed things up, right? So let's make that a little bit more concrete. Let's say we have a path here, and let's say the distance to E is 5. So let's say that this is a path of length -2, right? The shortest path to C is now this, right? It's now the path to E and then the path to C. But here's the problem. When we run Dijkstras, we assume that our paths are in ascending order. So we're going to say once we pop C, that's the shortest path. So again, we're still going to check any paths of length 1, any paths of length 2, any paths of length 3? No. Any paths of length 4? This is the first time we encounter, right, C. So we're going to assume that, okay, there are no shorter paths here because if there were, we would have found them already. However, that's not actually the case because you'll see then we will check for paths of length 5, then we will check for paths of length 6, and then eventually we're going to get to a point where we come back around here, and now everything's all messed up because we found a path that breaks our ordering, right? We found a path that C that is shorter than the previous path we found, and it came after that previous path, which doesn't make any sense. Okay, that is basically why we cannot have these things. If you feel like this all went way over your head, don't worry about it. This is just like broad application stuff, but I hope that maybe this gives you a little bit of a better understanding of these algorithms.